Now, we're going to talk about vision transformers, which is a powerful new approach in deep learning. This architecture takes ideas from transformer models, originally developed for natural language processing, and applies them to the field of computer vision. Let's explore it in 3 parts. The vision transformer architecture. How does the multi-head attention mechanism improve image processing in ViT? The role of positional embeddings in ViT. The vision transformer works by processing images differently than traditional models. Instead of looking at an image as a whole, it divides the image into smaller patches and treats these patches like a sequence of data. This approach allows the model to capture the relationships between different parts of the image and understand long-range dependencies in the visual information. The ViT model consists of several key components that work together to process images. Let's go through each one. The first, input representation. Unlike traditional convolutional neural networks, CNN, which process images using convolutions and pooling to extract features, ViT treats images more like sequences of tokens, just as transformers process sequences of words in text. 1. Image patch partitioning. We split the image into small, fixed-size patches. For instance, if we have a 224 × 224 pixel image, we might divide it into 196 patches, each 16 × 16 pixels. This way, the image becomes a collection of small pieces. 2. Flattening patches. Each patch is then flattened into a one-dimensional vector. Imagine each patch has a size of 16 × 16 pixels with 3 color channels, RGB. Flattening it turns that patch into a single long vector. 3. Linear projection. Now, each flattened patch gets passed through a linear layer to be projected into a vector of a fixed size, say 768. This is similar to how words in NLP are turned into embedding vectors. 4th, position encoding. Since transformers don't inherently understand the spatial arrangement of these patches, we add position encodings. These encodings are learned during training and tell the model where each patch is located in the image. This allows the model to understand the layout of the image. So, after all this, the input to the ViT model is a sequence of patch embeddings, each with position information attached. This sequence can be represented as n × d, where n is the number of patches and d is the embedding dimension. The second, transformer encoder. The core of the ViT is the transformer encoder, which processes the sequence of patches through multiple layers of transformer blocks. 1. Multi-head self-attention. The self-attention mechanism allows the model to focus on different parts of the image at once. It does this by computing attention weights, which tell the model how much focus to put on each patch relative to others. In ViT, multi-head attention means the model can look at the image from several different perspectives at the same time, capturing both local and global relationships between patches. 2. Feed-forward network. After the attention mechanism, the output is passed through a feed-forward network, a couple of fully connected layers. This helps transform the data further before it's passed to the next layer. 3. Layer normalization and residual connections. These techniques are used to stabilize training. Layer normalization normalizes the data at each step, and residual connections allow the model to bypass some layers, helping it train more effectively. The third, classification head. After processing the input through the stack of transformer layers, the output is a sequence of embeddings representing the patches. To perform the classification task, ViT uses a classification token, CLS token. First, a special token, like the CLS token used in NLP transformers, is added to the sequence of patch embeddings before feeding it into the transformer encoder. This token aggregates information from all patches and is used to produce the final image classification prediction. Then, in some variants of ViT, instead of using the CLS token, the output embeddings are pooled, typically using global average pooling, where the average of the patch embeddings is taken as the final representation of the image. For final classifier, the output of the transformer encoder, either the CLS token or pooled embeddings, is passed through a fully connected, dense layer to generate the final classification logits. The fourth, training and optimization. Vision transformers are typically pre-trained on large datasets using supervised learning. Once pre-trained, they can be fine-tuned for specific tasks like image classification, object detection, or segmentation. Unlike CNN, which perform well with smaller datasets due to their inductive biases, local receptive fields, translation invariance, ViT requires large-scale data for optimal performance. The fifth, advantages of ViT. 1. Scalability. ViT has shown to outperform CNN when trained on large datasets, particularly in image classification tasks. 2. Long-range dependencies. The self-attention mechanism captures long-range dependencies in an image, allowing it to model global contextual information more effectively than CNN. 3. Flexibility. The transformer framework allows for easy integration with other architectures and models, enabling more advanced vision language models. In summary, the vision transformer is a novel architecture that applies the transformer model to computer vision tasks by representing an image as a sequence of patches. The core components are the patch embeddings, position encodings, and transformer encoder, which learns the global dependencies between image patches through self-attention. While ViT achieves state-of-the-art performance on large datasets, it requires significant computational resources and large amounts of data to reach its potential. Now, let's break down the multi-head attention mechanism in the vision transformer and see how it significantly enhances image processing. This mechanism is crucial because it allows the model to focus on different parts of the image simultaneously, enabling it to capture complex relationships and understand the image in a more holistic way. Here's how it works. The first, capturing long-range dependencies. In traditional convolutional neural networks, the model processes images by applying filters to small regions, or local patterns, such as edges or textures. This works great for recognizing small-scale features, but it struggles with capturing long-range dependencies, the relationships between distant parts of an image. For example, recognizing that a person's face is related to the person's hand, even though they are far apart. In ViT, each patch in the image can attend to every other patch, so even patches in distant corners of the image can exchange information. This ability to capture global relationships makes ViT more effective in understanding the full context of the image, no matter how far apart the relevant features are. The second, parallel attention, multi-head attention. Now let's talk about multi-head attention. This is where the power of ViT really shines. 1. Multiple attention heads. Instead of using just one attention mechanism, ViT employs multiple attention heads. Each head looks at the image from a different angle, or perspective, and calculates its own attention distribution. This means the model can focus on various aspects of the image at the same time, such as texture, color, or spatial arrangement, allowing it to process the image more efficiently and with richer detail. 2. Capturing diverse aspects. For instance, one attention head might focus on fine details like edges or textures, while another could focus on high-level semantic relationships, such as object interactions or larger patterns in the image. This parallel processing helps the model capture a more comprehensive understanding of the image's features. The third, improved representation of image features. In traditional models, each feature, like a patch, is typically represented based on local information. But in ViT, self-attention allows each patch to update its representation by considering the relationship to every other patch. So, each patch gets context from the entire image. For contextualized patch representations, take an image of a cat, for example. The model learns relationships such as the ears are above the eyes, the whiskers are near the nose, the tail is usually at the bottom right. Through attention, each patch in the image adjusts its understanding based on the context of other patches. So, the patch representing the cat's body will update itself with the knowledge of where the head, ears, and tail are, making the overall representation much richer. The fourth, dynamic attention weights. What's fascinating about the multi-head attention mechanism is that it doesn't treat all parts of the image equally. The model assigns different weights to different patches based on how relevant they are for the task at hand. First, dynamic focus. For example, in one image, the model might focus on the background to understand the broader scene, while in another image it might focus on specific objects of interest for classification. Then, the attention weights adapt during training, so the model learns to focus on the right parts of the image based on context, whether it's for identifying objects or understanding spatial relationships. The fifth, reduced bias toward local features. One limitation of CNN is that they have a built-in bias toward learning local features because of their convolutional filters. While this works well for many tasks, it's not ideal when understanding long-range dependencies is critical, like recognizing a person's pose or the relationship between distant objects. With ViT, the self-attention mechanism helps reduce this bias. The model can pay more attention to the global context, making it better suited for tasks like object detection or understanding complex scenes. The sixth, improved generalization. Thanks to multi-head attention, ViT processes the image in a more holistic way. Instead of just focusing on local features, it learns to consider the global structure of the image, which helps it generalize better across different tasks and images. The seventh, handling complex spatial relationships. ViT's attention mechanism is also great at learning complex spatial relationships between different parts of the image. 1. Object parts. For instance, the model learns that the legs of a person should be below the torso or the face should be above the neck. 2. Contextual relationships. It also understands how different objects relate to each other. For example, it might learn that a person is sitting on a chair or a cup is on a table. In summary, through multi-head attention, ViT can handle complex relationships like these by allowing all patches to communicate and adjust their understanding based on the entire image context. And by leveraging multi-head attention, ViT can outperform traditional CNN on large-scale datasets and tasks that require understanding the global context of an image. This makes ViT a powerful tool for image classification and beyond. Then, in the vision transformer architecture, positional embeddings are crucial for preserving spatial information in images. Since transformers, by design, are position agnostic, they don't inherently understand the spatial relationships between elements. In ViT's case, the image patches. An image has a specific spatial structure, like left to right or top to bottom, and positional embeddings provide the transformer with the necessary context to understand where each patch is located within the original image. Let's break this down. The first, transformers are position agnostic. In traditional transformers, such as those used in NLP, the model processes a sequence of tokens, like words in a sentence, without knowing their positions. The tokens are treated independently, and the transformer doesn't naturally understand where each token falls in the sequence. In ViT, an image is split into non-overlapping patches. Think of cutting the image into small squares, and each patch is flattened into a one-dimensional vector. These vectors form a sequence, but this sequence lacks any information about the patch's position in the two-dimensional space of the image. The second, how positional embeddings work. 1. Patch embeddings. When the image is divided into patches, each patch is flattened into a vector, which is then projected into a higher dimensional space. These vectors form the patch embeddings. 2. Position encoding. To give each patch a sense of its position, a position encoding is added to the patch embedding. This position encoding is essentially a vector that represents where the patch is in the image, like coordinates in a two-dimensional grid. 3. Addition of position embedding. The patch embedding and position encoding are combined, added together, and this enriched embedding is passed through the transformer. As a result, each patch embedding now contains both content and spatial information. The third, types of positional embeddings. 1. Learned positional embeddings. In ViT, positional embeddings are typically learned during training. These are trainable vectors similar to word embeddings in NLP models. and the model learns to represent spatial locations based on the specific dataset and task. 2. Fixed positional embeddings. Alternatively, fixed position encodings, often sinusoidal, can be used. This approach is inspired by the original transformer model used in NLP tasks, like BERT. However, ViT typically uses learned positional embeddings to provide more flexibility in capturing the spatial structure of images. The fourth, spatial structure and relationships. 1. Retention of spatial structure. Positional embeddings ensure that the ViT model preserves the relationships between patches. For example, patches that are close to each other in the image, like top left and top right, should be understood as being spatially related, while patches far apart, like top left and bottom right, should be recognized as distant. 2. Global attention. The self-attention mechanism in ViT calculates attention scores between all patches. Positional embeddings help the model understand not only the content of each patch, but also its location relative to the other patches. This allows the model to understand the overall structure of the image, which is essential for tasks like object detection or scene segmentation. The fifth, interaction with self-attention. In ViT, the self-attention mechanism calculates relationships between every pair of patches. Without positional embeddings, the model would treat the patches as if they were part of a flat, unordered sequence, losing all the important spatial information that makes the image meaningful. By adding positional embeddings, the model can capture both local relationships between nearby patches and global relationships between distant patches, which is essential for understanding the spatial context across the entire image. The sixth, impact on performance. 1. Preserving spatial context. Positional embeddings are vital for ensuring that the transformer can interpret the spatial hierarchy and contextual relationships between patches. Without them, ViT would not be able to properly capture the spatial organization of the image, leading to poor performance on vision tasks. 2. Learning spatial relationships. By using positional embeddings, ViT is able to better capture both local and global spatial relationships, improving performance, especially when the model is pre-trained on large datasets. An example of positional embeddings in ViT. Let's consider a 224 × 224 image that is divided into 16 × 16 patches. This results in 196 patches. After each patch is flattened and projected into a high-dimensional space, such as 768 dimensions, these patch embeddings are combined with positional embeddings to form a sequence of 196 vectors, each of size 768. For example, the patch at the top left corner would have a distinct positional embedding compared to the patch at the bottom right corner. These embeddings help the model differentiate between patches and learn the spatial relationships. In summary, without positional embeddings, the vision transformer would treat the image patches as an unordered sequence, making it impossible to learn the essential spatial relationships required for most computer vision tasks.